Okay, let's begin. Welcome to you all here in the auditorium this afternoon and to all of you online too. It's our great pleasure to welcome Lee Hood this afternoon to speak to us. I'm going to tell you a little bit about Lee in a moment, but Lee was just telling me that he originated from Montana, from a town of 2,000 people and a high school class of 40. So, you know, from deep rural US, and then made the big suffered the big culture shock of then moving to Caltech in California. He did his MD in the Johns Hopkins University School of Medicine. Then he did his PhD in Caltech and was a faculty there for about 15 years, or actually more than that, being chair of biology from 1967 to 1992. And during that time, Lee and his colleagues developed 4 DNA sequencer and synthesizer instruments, which paved the way to the Human Genome Project. During the course of his time at Caltech, he worked on the complex mechanisms of antibody diversification. And then in 1992, founded the Department of Molecular Biotechnology at the University of Washington. And subsequently, in 2000, founded the Institute of Systems Biology in Seattle. Amongst his many scientific achievements, he's also co-founded 17 biotech companies, including multiple familiar names such as Applied Biosystems and Amgen, and has won many awards, including the Lasker Prize, the Kyoto Prize, and the National Medal of Science, and is a member of the National Academy of Sciences in the US. Lee is currently CEO of Phenome Health and professor at the Institute of Systems Biology. Lee, you're very welcome indeed. You have the floor.
Pleasure to be here. And what I'd like to do is to give you a very brief survey of how I've evolved to start thinking about precision population health, which basically is lots of measurements on lots of people. And what can it tell us about individual humans? That's the essence of what we'll talk about today. I've started this organization called Phenome Health, and it is pushing a second genome project, which we've named Beyond the Human Genome, and you'll see just why that is in a few moments. Long term, we'd like this program supported by the government across the 10-year period. And in the short term, to get started before we get government funding, we're applying precision population health to major health diseases. And the first one I'll talk just a little bit about, which we've already gotten started on, is type 2 diabetes. So what I'm going to talk about, and this is just to give you a context for how I thought about human complexity and ultimately how I'm viewing medicine of the 21st century. Namely, it's a series of paradigm changes I've either helped initiate or at least participated in. And of course, the first one you've already heard about, bringing engineering to biology. And over the years, we developed 6 different instruments. We started 3 companies to commercialize them. All of them have been successful even today, and all of them are being used. And of course, the most powerful has been automated DNA sequencing, which actually got me invited to the first meeting ever held on the Human Genome Project in Santa Cruz in 1985, where 12 of us came together to debate the merits of the Genome Project and came to 2 interesting conclusions. One, it could be done. It was complex. And 2, we were split 6-6 on whether it was a good idea. Those against it really felt there was a danger of big science destroying small science. And of course, that didn't happen. For me, when the human genome was done, what it made possible was access to human variability that you could correlate with wellness and with disease phenotypes. And we'll talk about that in the future. My lab became very big at Caltech because we tried to bring together all the different cross-disciplinary flavors for technology development. And this led me to the idea I would like to develop at Caltech a cross-disciplinary department. And of course, the biologists were opposed. Everybody else thought it was a good idea. But in small places, veto power is dominant always. And I ended up moving to the University of Washington to start the first cross-disciplinary department at the medical school there at the behest of Bill Gates, who put up the money and endowment that was necessary for that program. And it was enormously successful. Phil Green wrote the algorithms that drove quality control assembly. Rudy Ebersol and John Yates really pioneered the field of proteomics at that time. And we developed the inkjet technology for very rapid DNA synthesis that Agilent still uses today and so forth. But it was clear that the bureaucratic structure of a large state university was not felicitous for starting a new form of biology, namely systems biology. So in 2000, I resigned and started the Institute of Systems Biology. And of course, this is all about taking a global and holistic view at biology. It's about converting large data into biological networks that underpin physiology and mechanism and so forth. And it's about applying these things both to biology, and we had a whole series of seminal papers on that. But we started thinking about medicine at that time. And that, in fact, is when I first really pushed the idea that healthcare should be the 4 Ps: predictive, preventive, personalized, and participatory. The first 3 Ps are science, and I'll argue we know how to do much of that today. The 4th P, how you persuade patients and the healthcare system to participate in a healthcare that's focused around wellness, is a much tougher initiative. What was really interesting is in this period of the early 2000s up to 2006 or 7, we were developing a series of technologies and strategies that I had difficulty getting funded at NIH because they were thinking more traditionally about these kinds of things. And I had the good fortune to persuade the state of Luxembourg, and I won't go into how I persuaded them, but they gave us $20 million a year for 5 years and to invent the technologies of P4 medicine. And what that led to very quickly was the ability to think about precision population genetics. And we started with a 108-person project where we did lots of data on those patients every 3 months for almost a year. And to get it funded, I did go to NIH in 2013 and talk with Francis, who made this famous quote to me: "NIH is interested in disease, not wellness. We'll never fund a project like this." So we had to figure out how to get it funded. We did. And the funding of the 108-person project then led to the creation of a company called Aerovale that applied what we called scientific wellness to consumers to optimize their wellness and let them avoid disease. And we'll talk about that in just a few moments. And the final change actually came when I was asked to become chief science officer at Providence, a very large healthcare system centered in Seattle. And it gave me the chance to push forward what evolved into this idea of beyond the human genome, where we amplified the 5,000 individuals we looked at in Airvale, 200-fold to suggest that we look with genome-phenome analyses of the order of 1 million people over a period of 10 years. And of course, the basic idea was, rather than sequence a single genome in 13 years, as the first one did, Beyond the Human genome would propose to do this across a 10-year period using genome and phenome. We'll explain that in a moment. And then convert these data into actionable possibilities. And I'll talk operationally exactly how we did that. And to seek government funding to set this project up over the 10-year period of time. And we're now exploring with industrial partners the possibility of a series of data-rich clinical trials on major chronic diseases. And we've started with diabetes already. Phenome Health is a nonprofit I started who has assembled 7 partners that will let us carry out this kind of initiative. I'll describe that in just a few moments. And of course, what Beyond the Human Genome is about is longitudinal phenomics, the ability to assess individuals across their lifetime in principle. The genome, relatively invariant throughout your life. The phenome, of course, is the integration of lifestyle, of environment, and the integration of genomics and how they impact each of us at each instance of our life. In a sense, we all have a multitude and infinitude of different phenomes, and we can assess those phenomes in many ways. And we do it traditionally by looking at blood analytes, the gut microbiome, digital health devices, and the like. I'll describe this in more detail in just a moment. And the long-term vision is this has pushed us toward what we call the science of wellness and prevention, in that we now have the ability to access the health status of an individual across their lifetime and to optimize it. And that trajectory, that health trajectory, has 3 different phases. A wellness phase, most of us start with, a transition phase where all of us go from wellness to disease, and most of us return to wellness and go back and forth a multitude of times before our life ends, and then finally disease and its progression. And what I'll say is we can optimize in really interesting ways wellness now, far beyond what people ordinarily think about it. We can identify at the earliest detectable stage early wellness to disease transitions and use those blood biomarkers to think about designing therapies to reverse disease before it gets started. And finally, we can apply precision medicine techniques to dealing with extant disease and so forth. And what we plan to do in the future is to be able to extend our health trajectory where we're in a continuous state of wellness by reversing as they appear the various transition states and so forth. So this is the output of what is necessary to achieve this P4 medicine I talked about earlier. And I'd argue if we succeed, it's certainly the largest paradigm shift in the history of medicine. We've got 2 demonstration projects that I think provide a proof principle for population health. So one is the Airvale population of 5,000 deeply genotyped and phenotyped individuals, and that's what we're going to spend much of the lecture discussing. A second thing we've recently brought in is the idea of brain health and using digital measurements of a whole variety of different types to assess cognition and the health of the individual with regard to cognition, and actually the ability to replace losses in cognition through appropriate games and functions and exercise. And our collaborator, Michael Merzenish, in this effort started a company called Posit that does this. And they've now initiated more than 250 trials, 10,000 people, in just fascinating examples of how the brain is flexible and you can reconstitute lost cognitive kinds of functions. For the Airveil program, which I'm going to talk about, we did whole genome analysis. We did 1,200, the quantification of 1,200 analytes in the blood twice a year. We analyzed the microbiome twice a year. And then we did digital health measurements with Fitbit and other devices. These data then went into a cloud for each individual that could be assessed and analyzed to identify actionable possibilities uniquely relevant to certain individuals that, if acted upon, could improve wellness and avoid disease. And an actionable possibility, for example, I'll give as one for my own experience. I was in this program. Very low vitamin D, actually, for about 80% of the people present in this study. My own, I tried to supplement 1,000 international units. I hadn't been taking any vitamin D prior to this, and it made no difference whatsoever. When we analyzed my genome, we found that there were 2 variants, each of which could block, in part, the uptake of vitamin D. And it meant for a person with those 2 variants, you needed to take very high doses of vitamin D, 15,000 international units. And now I maintain at about 5,000 international units, and I can keep the thing level. So the integration of the genome data with the integration of the blood data led to an actionable possibility. And Airveil generated of the order of 200 of these, focused primarily about wellness as required by the FDA for programs like that. So what these 5,000 data clouds in Airveil then gave us to do is the ability to, in a sense, look at the dark matter of wellness and figure out really what it was all about. And I think in many ways, it's very much like what the Hubble telescope did in exploring the heavens and structure and evolution of the universe that those studies actually have revealed and displayed. So one interesting possibility was we could take the data, and again, I'm showing this from the smaller group. It's easier to show that data. And we were able to demonstrate, if you took the 6 types of data and look for correlations with data bits in each type against data bits in the other type, that we could see of the order of 3,500 or so correlations. And what you could do is look at those correlations and take the most interesting, go to the literature, and this led to a lot of the actionable possibilities and integration of different data types that emerged from this type of effort. The hairball that came from the 108 statistical interactions was reduced to about 70 multi-dimensional communities by essentially snipping the edges that had the lowest probability to reveal these discrete communities. And each of the communities had a fascinating related set of molecules that had an impact on the major entity we use to name the community. For example, in the case of cholesterol, there was a positive interaction with vitamin E and a strikingly negative interaction with thyroxine. And what was interesting is at the time we did these correlations, we were able to show that Lilly was actually in the final stages of a clinical trial using thyroxine as an anti-cholesterol drug. So the point is, the 70 communities correlated with physiology and they correlated with pathology, and they gave us a statistical approach to biomarker and drug target discovery that was really different from what kinds of things that had been done before. We then studied not 500 proteins in the 108 individuals, but 35,000 proteins. And the correlations of these 5,000 proteins went up to 35,000, a tenfold increase that was in proportional to the number of features that you saw. So as with systems thinking, the more global you can make things, the more information you're able to gain and so forth. There are two complementary kinds of wellness. I think this most of us now know. Traditional wellness, and there are lots of companies out there that practice this in various ways. And I would argue the second is data-driven wellness. And of course, the actionable possibilities can emerge from the genome, they can emerge from the phenome, or they can emerge from the integration of different types of data. And the really important thing is the data-driven scientific wellness enormously enhance what you can do with traditional wellness. And the company Zoa showed beautifully how by learning about the gut microbiome and blood analytes, you can profoundly deal with complications that could be leading to diabetes and the like. And the same is true of exercise, same is true of sleep. And I suspect the same will be true of brain capacities in the end. So the idea with the actionable possibilities is that if you're willing to follow them and use the ones that are relevant to your own personal status, you can essentially move yourself up this ladder of wellness from, I would say, typical people are probably in the lower 30% or so of their wellness to a position of the wealthy. These are people, Eric Topol demonstrated 1,000 or so individuals in their 90s that had never been sick, never taken a drug, and were mentally and physically capable. And that, of course, is what we'd like to be able to do. And that requires then this lifelong journey of healthy aging to remain mentally and physically active up until your 90s and so forth. So wellness is one aspect of this, and we call this scientific wellness or quantitative wellness to distinguish it from the more traditional type of wellness that we have here and so forth. So what about then the science of wellness from a very, very different dimension then? So in the population we had here were people ranging in age from 21 to 93. And we were able to show in more or less a linear fashion as people aged, the envelope of control of the expression of the three classes of blood analytes broadened significantly. And that was true of clinical chemistries of proteins and of metabolites and so forth. And in a sense, we could use this broadening of that to develop an algorithm that said, it isn't quite so, but it's almost so. Those people whose envelope didn't broaden nearly as much are aging better than those people whose envelopes broadened very largely. And we were able to develop a classic algorithm that mirrored these effects very nicely and gave us a metric for biological aging. That is the age your body says you are, as opposed to the age your birthday says you are. The further you're below your birthday, the better you're aging. And we were able to show beautifully that people in Airvale who stayed with the program over the 4-year period, on average, women lost 1.5 years of biological age per year they stayed in the program, and men lost about 1 year per year they stayed in the program. But there were other kinds of remarkable variables too. For example, we had 40 trivial and significant diseases that we could look at and in this population, and essentially every one of them, the biological age of the individual with the disease was greater than its chronologic age. And in fact, those that had diabetes averaged 6 years older than their chronologic age. And we looked, interestingly enough, unfortunately, just at one very severe COVID patient. And this individual's biological age was 20 years greater than their chronologic age, and the individual died. So we never found out what the reversal was. But the other thing that's interesting is we used metabolites to develop the algorithm, and these metabolites actually gave us insights into the biological age of various organs, like your immune system and your kidney and your liver and so forth, as opposed to your global age. And so you could focus then on particular organs that really pulled down your global biological age. And because we used both proteins and metabolites, we were able to identify the themes that seem to indicate more rapid aging than is appropriate. And they had to do with metabolic possibilities, inflammatory possibilities, and actually the acquisition of toxins and so forth. So you could use these various features in this biological age metric to optimize for the individual, their biological age. So scientific wellness and healthy aging were two aspects of the science of wellness. Now, the science of prevention, of course, in part comes about from looking at polygenic scores, and with whole genome sequence, being able to convert each individual to a risk for that polygenic score. And here I show you the polygenic score for LDL cholesterol in individuals that aren't using statins. And what you can see is cholesterol goes up in a very linear fashion in accordance with increasing risk. And what we demonstrated beautifully in this population was if you're at high risk for LDL cholesterol, which is a proxy for heart disease, only statins will bring LDL cholesterol down. If you're at low risk and have high cholesterol, diet and exercise bring it down beautifully. And this to us, with one other example I could mention, suggests that we in the future will want to know genetic risk and deal with high risk and low risk people differently. And of course, with high risk people, we can follow them carefully to detect the earliest transition to disease and try and reverse it. And of course, what is really interesting about that is it leads to a very interesting kind of experiment now, where we took 54 different polygenic scores, converted them to genetic risks. We took the 1,000 analytes that we'd measured twice a year, and we compared the analytes against the population of increasing risks. And in the left over here, you could see that the analytes generally linearly increased or linear decreased in accordance with the increasing genetic risk. And that was true for all of the diseases. And the analytes that increased or decreased, interestingly, turned out to be very related to the disease process itself. So we were able to see, as I said, 800 analytes that correlated with these 54 diseases. And these analytes and their changes gave us insights into molecular pathophysiology and in some cases therapies. And I'll show you a potential example in just a moment. So the individuals at high genetic risk invariably displayed dysregulation in the same kind of analytes, those people that actually had the disease itself. And what this means is you can use whole populations to study these genetic diseases in absolutely fascinating ways. And this genetic risk is a wonderful proxy for prodromal disease, and we can essentially study its characteristics and learn, even at that stage, can we begin to accommodate the risk that is reflected in the genetics. And an interesting example is increasing risk for inflammatory bowel disease shows a striking decrease in blood cysteine. And of course, the reason that is interesting is inflammation is a very central part of this disease. And of course, cysteine is really a key analyte in the production of glutathione. And of course, glutathione is a very effective antioxidant. And we're beginning to set up some trials to see if that makes a difference in these high-risk people in the context of their disease and so forth. So there's an enormous amount of information here to go back and be able to look at these diseases in these very, very different kinds of contexts. So the final point I'd make almost in this set of Aravale analyses is when we looked at all of the individuals over this 4-year period, 167 transitioned from wellness to disease. And we took 10 of the individuals that transferred to various kinds of cancers, and we looked at blood analytes in blood draws prior to the clinical diagnosis. And for all 10 cases, we're able to show protein outliers that were way off the mean for the Aravale population at that particular point in time. These clearly indicated that a transition had occurred. And for some cases, the transition clearly occurred at least 5 years prior to the clinical diagnosis. So the hope is we can use these biomarkers to identify individuals that have had the earliest transition, and together with academics and pharma can begin to attempt to determine therapies that would reverse these transitions and avoid the manifestation of chronic disease. One of the really interesting biomarkers that came out of these studies was one that's called CCAMS5. And it was fascinating because in the 3 cases that we saw this cancer, it forecast in these individuals metastatic disease in a way no other biomarker did. So you can use this kind of approach to get biomarkers that can deal with trajectories, that can deal with transitions, and can deal with future state changes, such as metastases. So I think it's going to enormously broaden how we think about biomarkers. So the top 2 things are the science of wellness. The bottom 2 things are the science of prevention, genetics, and the transitions. And recently we've submitted a paper on metabolic BMI And again, this is a metric we'll be using for all patients in the future. And the advantage of metabolic BMI over the classic traditional measurements are twofold. One, it responds to changes in diet and exercise much more rapidly than traditional measurements do. But equally important is in the traditional measurement, if you're an athlete heavily muscled, you appear to be obese. And this separates those beautifully from one another. So we think this is going to be a very powerful metric for measuring metabolic states in the future. I'll show you where we want to do that. I just want to say a word about brain health. We could give a long lecture on all the things that Merzenich has done, but I think the really important thing is he has a digital approach of 40 different kinds of measurements that assesses 25 different cognitive features. And what he got the Kevley Prize for demonstrating was the enormous plasticity of the brain. And in humans, what he was able to show you is that individuals' cognitive abilities rose to a maximum in the mid-30s, and for almost everyone decayed thereafter. And he was able to take of the order of 1,000 individuals at 80 years old and restore their cognitive abilities near what they should have been in their mid-35. So you can restore lost cognitive functions. And he can do that for prodromal disease traits, stress and drug addiction, PTSD, and some of these other things in absolutely fascinating ways. Brain health is really going to be a future important aspect of your overall health. And the final area I'll talk about is the gut microbiome, very popular these days. And of course, the one thing we do know is diversity is really king. Your gut microbiome should be as diverse as possible within boundaries and limits. And what we were able to demonstrate is you can get a very accurate measure of your microbiome diversity from the quantitative measurement of 11 analytes, 11 metabolites in your blood. And the reason this ability is important is it lets us go in the future and do retrospective studies where we have blood samples and we can estimate how the gut microbiome has changed across wellness to disease transitions and disease transitions within the disease itself. And it's clearly going to be a really critical part of optimizing our wellness in the future. And again, this company Zoe has been a wonderful demonstration of that. But the final point that I would say, one really interesting study we did was to study 9,000 individuals that ranged from 60 years of age up to 80 plus years of age, 85 years of age or so, and to show that if you are a healthy 80-year-old, two profound changes occurred in your gut microbiome. One was the core microbiome that all of us have in our 20s and 30s was completely lost, and it was replaced by a microbiome that was uniquely different for each healthy 80-year-old, as if your microbiome was being selected by what your own needs were in longevity. In contrast, if you were unhealthy, you didn't lose the core microbiome and you didn't at all develop this unique diversification. And we compared the population from 80 to 85 over a 5-year period and showed that if you're in the healthy population, or if you're in the unhealthy population, you were 4 times more likely to die during that period with the unhealthy microbiome. And of course, what's cause and what's effect is not at all clear here, But one of the things we are thinking about is how you can manipulate the gut microbiome to mimic the kind of microbiomes we see in healthy 80-year-old individuals. Now, the reason the million-person project is going to be so important is, one, it's going to give us overwhelming proof that we can apply these principles of wellness and prevention to individuals and improve the quality of their health. And number two, we're going to be able to prove it saves the healthcare system enormous amounts of dollars. So the science of wellness is the things we've talked about, the optimizing body and brain health with actionable possibilities, optimizing one's aging, optimizing cognitive brain health, coming to understand what you need to optimize the gut microbiome, and how do you put together in an integrative fashion and uniquely push the integrated health of body and brain and the microbiome itself. And the science of prevention is looking at the genetics and dealing appropriately with individuals, looking at the transitions and reversing them. And if we can begin to reverse it even for most of the major diseases, in the US, 86% of our healthcare dollars are spent on chronic diseases. So here's an area with potential for enormous savings. And digital brain diagnoses and so forth, I think will transform brain health for actually all of us. So with the million-person project, we think will bring in thousands of new actionable possibilities that will in fact have to be delivered by AI. From the point of disease and precision health and so forth, we've already started with Alzheimer's. And looking at blood analytes, we can classify Alzheimer's into at least 6 different subtypes, some of which are strikingly different from one another. For example, people in the South who live in houses that have a lot of black mold inevitably get horrible Alzheimer's disease, which if caught appropriately early and you move out of those houses and get away from the black mold, can beautifully be reversed. We're going to look at genetic risk. There are 3 ways to do that. Family history is an interesting one, and I'm going to show you an example of that in just a moment. I mean, we're also interested in the whole question of digital twins, and we've made a beautiful model of digital twins for Alzheimer's, which operationally brings top-down physiology and mechanisms together with bottom-up biochemistry and assimilates most of the data we have in Alzheimer's in a computational model that then can look at the data from individuals and make assessments about where they are with regard to Alzheimer's. And finally, there are interesting multimodal therapies that offer, I think, real promise for the future, both with the reversal of early stage Alzheimer's and the prevention, if we can set up clinical trials to detect Alzheimer's at the earliest state. And because of metabolic PET scans that have been done early in individuals that gone on to get Alzheimer's, our guess is we'll be able to detect people getting Alzheimer's some 10 to 15 years before a clinical diagnosis can be made. And of course, that'll be really transitional. Here's a 5-generational family, lots of history of Alzheimer's. The lower 3 generations of the family, there are 43 complete genome sequences done. We've mapped onto these ApoE4, the dominant gene that predisposes to Alzheimer's, and we've mapped on the best polygenic scores for Alzheimer's. And you can see that these two, as you know, segregate in independent ways. But more than that, we can follow the independent segregation of some of the key variants in the polygenic score in the segregation, genetic segregation in these families. And that gets you to interesting genes and interesting mechanisms. A big part of what we want to do in the Million Person Project is have many families, because family analyses enormously enhance the understanding of individual with regard to isolated studies. And finally, I'll just show you for the most dominant feature, homozygous individuals for ApoE4 in 4 different classes of populations. You can see in Caucasians, if you're homozygous for ApoE4, by the time you're 65, you have a 60+% chance of getting Alzheimer's. In Japan, you're 3 times as likely to get Alzheimer's. And for the Hispanic population, I mean, strikingly enough, the ApoE4 gene seems to make no difference whatsoever. And this underscores the imperative importance of equity and diversity and equality in the data that generate the insights that provide wellness in the future. And we plan to be able to reflect that diversity appropriately. So from the Airvale population have come of the order of 13 really high impact papers and very good journals that verify what I've talked about here and things that I haven't talked about. But where are we today in the Beyond the Human Genome study? Number one, we're going to generate data that includes now the brain health that I talked about, electronic health records, and these are really key for reasons I'll talk a little bit later about. And then we're going to do social determinants of health and patient outcomes. So we'll be able to integrate these, quote, 7 different types of data, I think, in really a unique way. The partners that we've acquired in creating the infrastructure for doing this are Guardian Research Network, with an organization started 10 years ago, which interfaces with 140 hospitals in the South and Southeast. And what they've done is, one, consented the 30 million patients that are in those hospitals for future studies like the Million Person Project I'm talking about here. Number 2, they've learned to extract electronic health records from all of the healthcare databases, major ones in the US, and they have both structured and unstructured data beautifully included. Unstructured is doctor's notes and path reports and radiation reports and the like. And number 3, they are in 13 states. They lie across large African-American and Hispanic populations, and will include those in proportion to what they are in the US population as we recruit the Billion Person Project. Posit Science is the brain health we've talked about. Technicity has, with us in a very short 3-month period of time, developed a computational platform that guides and directs virtually all of the phenomena we need for education and acquisition of patients, the acquisition of samples and placement in the biobank, sending them from the biobank to the data vendors, then the reacquisition of data in the cloud, and then, of course, being able to standardize all the data. That is critical if you're to compare different batches, and finally, analyze and integrate the data. So that is the platform that we're in the process of putting together. For ISB, they're providing a whole variety of different technologies that I'll talk about at the very end of my lecture. Bioanalytica, a company that we spun out of ISB that will do the generation of multi-omic data along the lines we're talking about here. Deloitte is recruiting partners to help pay for this project in the context of high data dimensional clinical trials, and Google has agreed to give us access to 4 of their major companies in Alphabet. So search, cloud, digital health, Fitbit, and hyperscale AI. And we'll talk more about that in just a few moments. We've explored partnerships with NIH, the All of Us program, DOE for technology and computation, and the VA, their million-person project. And I think there are good collaborations in the offing there. We have an outstanding advisory board. I've done a lot of lobbying in Congress, presented to them in December, and was, I think, very successful. But it isn't going to happen for a year or so because of all the obvious things that are happening, including the war. And finally, we persuaded an academic healthcare center to let us bring the science of wellness and prevention to their family practitioners to begin using this in the context of scientific wellness and healthy aging. What is unique about this project with regard to many of the other million-plus person projects is, one, we have many different types of data to be able to integrate together, as I've indicated. And 2, we will return actionable possibilities to patients. And I think we're going to generate, literally, as I said, thousands of new actionable possibilities. And with Google, we're thinking about how to deliver them with AI. We are going to be able, in the context of this effort, to identify biomarkers that let us identify drug responders as opposed to non-responders. And that's important. I'll show you that in a minute. That saves a lot of money. And finally, we're going to take on the 4 major chronic diseases that are largest in their impact on healthcare: heart, cardiovascular, cancer, and neurodegenerative. And we're going to stratify them and look at transitions. And I'll show you exactly what I mean by this in the example of diabetes. So we plan, for example, to take diabetes where a typical drug may give 10 or 15% of the patients working, and divide them into the subtypes that represent either different transitions and or different subtypes of diabetes, and look for each, again, with pharma drugs that can deal with them to 100% efficiency rather than a very low efficiency. And I think it's going to be a new paradigm for drug discovery and treatment. And we're actually setting up a new pharma company now that is going to use the enormous combinatorial potentiality of peptide drugs to be able to deal very rapidly and on a very large scale with the enormous numbers of targets that are going to become evident in this kind of trial. Just think about the 7,000 rare diseases that exist today, 80% of which are genomic in origin, and the 7,000 Mendelian recessives, many of which will be active in the heterozygous form. So, and then finally, looking at the 10 top selling drugs in the US today, it's appalling to discover that less than 10% of the patients respond to these drugs. And imagine if we could pick the patients out, give the drugs only to those that respond. In principle, you could save 90% of the $600 billion a year. Pharma might not like it, but it certainly would save the healthcare system an awful lot of money. So let's talk about precision medicine and integrated high data density diabetes trials and so forth. And this is something we're doing with Ralph Snyderman at Duke and his assistants there. And they have the hypothesis, not agreed upon by many, that there are 4 distinct transitions in the natural history of diabetes, and we're going to test that particular hypothesis. And we're going to do it in a very powerful way with deep immune phenotyping. So let me tell you really quickly how that's really transformed our ability to carry out an observational trial on COVID-19 and what that's led to. So we took 300 patients, we brought them in, took blood draws at admission at 10 days, that looked at the acute infection, and then 2 to 3 months that looked afterwards to see who had recovered. And we were able, with this deep immune phenotyping, to actually follow the trajectory of the disease, of drug responses and the like very, very nicely. So what is deep immune phenotyping? It's taking 5,000 single cell white blood cells at each blood draw and doing complete transcriptome analysis, in some cases epigenome analyses, looking at 250 cell surface molecules and 40 secreted molecules. This allows us to identify completely every cell type and its differentiation state. And of course, if you integrate across the 5,000 cells, you get a collective demonstration of relative contributions of innate and adaptive immunity and T and B cell immunity and the like. And of course, this is an amount of data that begins to approach what you do in sequencing a genome. And what's very nice about it is you can take this enormous data dimensionality and reduce it with a UMAP to 2 dimensions that allow you to identify beautifully the major cell types and their states of differentiation for white blood cells and so forth. And we can obviously quantify things in very effective ways. And this has really led to spectacular kinds of things. We can show at admission, there are 4 major types of patients. We can now show this with biomarkers, and by following immune profiles, we can show that 2 are in severe sets of patients and 2 in mild patients. And of the 4, only 1 at the time of convalescence has the immune system returned to normal. So that's the raw material for long COVID, obviously. And number 2, we can use the metabolite measurements in the blood and integrate them together with the transcriptome analysis of single cells and get the metabolic level of each of the cells individually. And this opens up new classes of T cells and B cells that are really very interesting. We can show that in long hauler patients, there are autoimmune phenomena that almost certainly underlie what long haul is. And this leads to interesting speculation about chronic fatigue syndrome and chronic Lyme disease and whether these aren't variations in the theme with long COVID. And those hypotheses can be tested. And in the latest Cell paper we published, there are at diagnosis 4 features that can predict, 1, whether you'll get long COVID, and to a certain extent, what type of long COVID you'll actually get. And that's, do you have lots of viral RNA, specific autoimmune antibodies, the activation of certain latent viruses, and diabetes is an enormous predictor of these kinds of things. So we plan to use in this chronic disease diabetes, this deep immune phenotyping together with genome analysis. But in addition, what we're going to do is take a retrospective study of the electronic health records, looking for clinical markers that will identify cells that are poised before transition points, individuals poised before these hypothetical 4 transition points, or subtypes. We can do it either way and sense these kinds of things. So what we'd like to do is 250 patients at each of the 4 subtype transitions and follow them for a 4-year period. So in 4 years, we look at the natural history of 15 to 20 years of type 2 diabetes. And we do genome, phenome, and deep immune phenotyping, and more recently, deep metabolic phenotyping. And that'll lead to disease stratification and or classification and patient stratification and identifying ultimately potential drugs that will be effective in dealing with these things. So the essence of the study is the retrospective view of tens of billions of patients gives us the 1,000 patients that will let us actually effectively carry out a prospective trial. And that's just an observational trial. And then in the future, what we'll be able to do is a third approach where we do manipulation clinical trial with drugs to see what works most effectively and so forth. So we're going to create in this program a data system, a biobank for hypothesis testing and biology analysis, platforms for education and recruiting, platforms for data acquisition, and platforms for data analysis. And those will all be integrated together seamlessly. We can deal with minorities. We're going to, and I'll talk about this in just a moment, use the most powerful new approaches for computational analyses of these kinds of data. And they are the platform I've talked about here, multidimensional data analysis, knowledge graphs, and we have 2 of those. Google has one with about 50 million nodes connected by features that tie together drugs and data and all of the different correlations one can make from the literature. With the digital twin models, again, taking all of the diabetes data that exists, either top-down physiological or bottom-up from the biochemistry, and using those as a filter to look at individual human beings. And this hyperscale AI, which Google and Microsoft both have, which is they've spent hundreds of billions of dollars on making computational engines that can do combinatorial calculations that are orders of magnitude greater than anything done by other kinds of machines out there. And their argument is this qualitatively begins to move you from simple correlations to much deeper insights if you can train the hyperscale AI in an appropriate manner. So in talking with Craig Mundy, who was number 2 at Microsoft, we've agreed that what would really be interesting to do would be to take hyperscale AI and inform it with 3 things: these big knowledge graphs that we have, the digital twin models that we have for certain diseases we might be interested in, and then all of PubMed. So in a sense, giving that to these deep learning machines would put constraints on the computational space they could search in interesting ways so that you could take the data from patients and make correlations, the likes of which you've never imagined before. And we're going to be trying this in the next year. So what I think I'll close with is saying this deep learning, which is what we're talking about, has manifested itself really marvelously in the ability to, after recognizing tens of thousands of patients' faces and everything, of recognizing the ability to take an individual and determine, for example, starting early how they age or starting late, how they could be pushed to get younger, or now you can start any place and go either kind of direction. So what we're playing with, other people are playing with, is the complete developmental pattern of slime molds and seeing whether similar kinds of predictions can be made from the developmental biology of a living organism. And of course, what we'd really like to be able to do this on is patients in the future. Can you project accurately transitions or aspects of transitions in this new regard using these very powerful deep learning kind of techniques? So with that, I'm finished. Be glad for questions if there are any.
Thank you very much, Lee, for that inspiring talk, huge numbers of ideas. Are there questions? Yeah.
Is it?
So yeah, I really like the idea of using, trying to find wellness for people, and having lots of data, very good. I guess my concern is over medicalization, and if you offer clinicians thousands of new ways to treat people, they may not be able to balance the harms from the benefits. And so how are you thinking of dealing with those things in the future, particularly as you were talking about going out to general practitioners?
I think what you have to do is deliver with AI to the physician in priority order the things that should be done. And then the physician and or the patient can decide whether they want to do one thing or 5 things or 10 things. I think that's all you can do. The other thing is educating patients and physicians about the importance of some of these actionable possibilities is really key. For example, with rare diseases, as we come to understand a lot of the genes that affect those, will have enormous insights on what we might do. And that is an actionable possibility you really want to take into account, because although with rare diseases, a lot occur early in development, some people are sick an awful lot of their life and they never quite figure out from that what it is. So I think all you can do is prioritize, and then it'll ultimately be up to the physician to be able to do this. The other thing I'm really intrigued with is in Aravale, what we were very successful in getting people to carry out the actionable possibilities at the top 10 of their list or so. And the way we did it is with personal coaches. Now, a personal coach could handle easily 100 individuals, but personal coaches are never going to scale. So what we're talking with several companies about is the possibility of getting personal avatars that can actually explain these things to you in very simple, to patients in this case, in very simple language. And frankly, the same could be done for physicians too in an educational kind of program. But, I think the only thing, I think the more you know about yourself, the better you're in a position to judge how you can optimize your health trajectory. So all we can do is prioritize things and let physicians and patients make decisions. The question of how you educate patients, how you educate physicians is really a serious one, because this is going to be a very different world for physicians. So we're starting to put together very simple courses to do this kind of thing now. But that's only going to scratch the surface of what we need if, we have 10,000 new, and if we get 10,000 new actionable possibilities, most of them are going to be rare. I mean, they're going to occur for very, very few patients. So it isn't it isn't quite as bad as it sounds, but there'll be a lot to learn.
You distinguished early in your talk between chronological age and biological age. Can you give us a little bit on how you measure biological age and how uncoupled biological and chronological age become?
So basically, the simple way to think about it is the way I described. In the population, as you age, your ability to control the expression of blood analytes gets more and more diffuse. And in a sense, those individuals who retain better control of their analytes than others are aging more effectively, and they're more like someone in their 20s than they are like someone in their 80s, okay? So we've transformed that to an algorithm that lets us do this by measuring 100 blood metabolites, basically, and to do a simple algorithmic calculation. And the reason we think this is valid is that we compared it against the Airvale population over this 4-year period. And as I said, it's really striking. For each male, you lose a year of biological age per year you stayed in the program. For each female, it was 1.5 years. And I had one of my closest friends actually use 10 years during this period of time. So the really interesting question is, how far can you push this down? And of course, we don't have enough data to say this really has improved our ability to live out and be functional in the 90s. That's going to take a while to do. But what we can say is phenotypically, I think almost all the people in the Airvale program were shocked and horrified it didn't make money. And that's in part because the blood phenomics was so expensive and everything. But they felt better. Many of them came to me and said, is there someplace I can go and get a program? I'm willing to pay anything it takes. So I think that's why I want to do this 1 million-person project and drive the cost of phenomics way down, as we did with the Genome Project over a period of time in DNA sequencing. And I think we can do it.
Okay, well, thank you very much again, Lee, for the lecture. That was absolutely amazing. And you can be another.
Thank you. Yeah, well, it was great to talk with you. Thank you. So.